All right, ladies and gentlemen, unfortunately, I am not in today, but I want to make sure that you're still making progress with our unit on further functions. The past couple of days, we've been uh, looking at how we can sketch graphs of rational functions, but realistically, at the end of the day, it's rare that we're going to ever have to make a super accurate graph of a rational function. And for most functions, what we're actually most curious about is what does the function do when it's right around the x-axis? That's really what we care about. So one trick that we have and one thing that we sometimes do is we make something called a sign diagram. Sign diagrams are actually the best way to solve inequalities. They're a wonderful tool. So what I thought I'd do is I'd walk you through a couple of them. And then you can look at my notes and you can try some problems that you'll get from the substitute, and you'll be absolutely fine. So before we jump in with a rational function, I want to do something with a function that maybe we're a little bit more familiar with a quadratic. So looking at this quadratic, the things that we want to know are where does it cross the x-axis. So if I look at this, I am going to have to split that middle term, right? So if I multiply the a times the c, I'd have negative 30, and two numbers that multiply together to be negative 30 but add to equal negative 1 are going to be negative 6x and 5x. Yeah, that split works. And then we'd have that minus 15 and the 2x squared. And then I'd factor what I can out of here, which looks to me to be 2x. And I'd have x minus 3. And factoring out of the second 2, I could get a 5 out of both of those, x minus 3. And as per usual, what I'm looking for is that these linear factors match. If they match, then I'm probably on the right track. So this will give me 2x plus 5 when I factor out that common linear factor, and x minus 3. So that means that 2x equals negative 5, x equals negative 5 halves, or x minus 3 is 0, x equals 3. Okay, so when we make a sign diagram, what we're going to do is we're going to draw in where this function crosses the x-axis. So let's call that 0, that 5, this negative 5. Negative 5 halves is 2.5, so I'm just going to make a dot, and I'm going to label that as negative 5 halves 0. And then I'm going to make another dot at 3, and 3 and 0. Okay, so now we have an idea where it crosses the x-axis. What I want to know about is what is this function doing before here. I want to know what's happening here. I want to know what's happening in the middle, and I want to know what's happening afterwards. Well, this is a quadratic, so we're pretty familiar with what that shape is going to be. But the way that we can check this is if I just pick a number in between here and here, and I evaluate it. So I just evaluate the function there. So I'm going to pick the easiest number I can think of, which is 0. And if I sub 0 in, so 2 times 0 plus 5, and all of that junk times 0 minus 3, well, if I look at that, that goes away, that goes away. I don't even care what the number is. I just want to know, is it above or below the x-axis? If it's a negative value, then it's going to be below the x-axis. So in between these values, it's going to be negative. If I substitute in, and I don't actually have to do this because I know what this function looks like, it's a parabola, but if I do that, then I would have let me put that 5 in, because I've got 5, which is after my 3. I would get 5 minus 3. I don't even have to evaluate this. This is positive. This is positive. I know that after it crosses that x-axis, it's going to be positive. Similarly, I know that it's going to be positive over there. So my sign diagram is quite literally just calling out where is this positive, where is it negative, and where does it cross the x-axis. So it just makes a real simple, easy way of doing that. And oftentimes we finish a sign diagram by just, I don't know, that looks like a pretty color. By just putting in a quick sketch. It doesn't have to be perfect, just showing that we know that this is a parabola and it's going to look something like that. And just to check that, I've got Desmos out. So if I did 2x squared minus x minus 15, sure enough, that's the parabola that I get. I can see that that's negative 2.5, and that's 3. So we've got ourselves a quick way of kind of sketching out what a function looks like. And what gets interesting with this is when we get higher degree polynomials, when we get a cubic or a quartic. We can do the exact same thing with a rational function. Now, the one thing about a rational function that a sign diagram doesn't capture is it's not going to see our y or our horizontal asymptote. Now we can find that pretty easy. It's just going to be 4/5, right? Because I just look here. And so I would have a horizontal asymptote at 4/5. And I'm not using a straight edge, and it's killing me just a little bit to show you me not using a straight edge. But that's my horizontal asymptote at 4/5. So what I need to know is, where does this cross the x-axis? Well, to find where it crosses the x-axis, I'm just going to set 4x plus 12 over 5x minus 10 equal to 0. And we like this because when we do this, I need to get rid of that denominator. So 5x plus 10, or 5x minus 10, I'll get that right. 5x minus 10, multiply that by both sides. And when we multiply by 0, that's going to go away. Sorry, I'm just going to do this work a little bit over here so I got some more space. All right, so that's going to give me 4x plus 12 is 0. So 4x equals negative 12, and x equals negative 3. So I know that this rational function, again, if I label this as my 0, my negative 5, and my 5, I know that this crosses the x-axis at negative 3, 0. Now, the other interaction it's going to have is we need to know where that vertical asymptote is. Well, the vertical asymptote is always, always, always found by setting the denominator equal to 0 and solving. So 5x minus 10 equals 0, 5x equals 10, x equals 2. So we're going to deal with our horizontal or vertical asymptote just by sketching in a dashed line that signifies that this is an asymptote at x equals 2. Now we just got to figure out what the heck this thing is doing. I know that it crosses there. I've got a pretty good idea. So again, just like with this quadratic where I substituted in values, I'm going to substitute in a value because I need to know what's happening here. I need to know what's happening here in between my x-intercept and my asymptote, and then I need to know what the heck this thing is doing after that. So again, I'm going to be lazy, and I'm going to put in 0. If I put 0 in for x, so I'm subbing in f of 0, well, those go away and I get 12 divided by negative 10, which is a negative number. So I know that in between my x-intercept and my asymptote, I'm negative. If I put negative 5 in, well, I know it has to cross the x-axis, and it's negative in between. So that means that prior to it crossing, it has to be positive. So this side of this function is going to follow its asymptote. It's going to go through the x-axis, and then it's going to disappear to infinity going towards x equals 2. Because we know what that is, we have a pretty good guess what is going to happen over here. It's likely going to be positive because it's got to be above that asymptote, right? But we can still check. So to check, if I just take 4 and I pick a number that's bigger than 2, I'm lazy, so I'm going to put 10 in because I'm just trying to see what's happening after the the vertical asymptote. Sorry, brain is foggy. All right, so if I look at that, I'd have 40 plus 12, which is 52, and then I have 50 minus 10, which is 40. Doesn't really matter what that is. All I need to know is that it is positive. So what this function, just a quick sketch of it would look like, is something like that. So I know this is a little bit messy, but I think you can see from this and looking at my notes how we can apply this creating our sign diagrams. I really hope that's helpful.